Okay, are we good now? Is this internet still going to be giving me problems? What's going on here? All right, folks, we should be back. Unfortunately, my internet connection at this new place is not very strong because I am on Wi-Fi rather than Ethernet. This is very annoying. Let's see. I should consider buying a very long Ethernet cable and just running it to the attic. Connection issues are such a pain in the butt. So, all right, let's give a moment for people to get back in. Sorry about that. My internet just crashed apparently. It's extremely frustrating dealing with rural Wi-Fi or rural broadband. But I'll go ahead and talk about, for the W is equal to A case, it's a very easy contradiction because we remember from the definition of locally linear, there is some delta such that A plus delta, everything in here is constant, right? Everything in here is some constant value. And because everything in here is some constant value, well, that means that W fails to be an upper bound on S, right? Because everything in here is constant, that means that every single value in here is an element of big S. But if A is equal to W and W is supposed to be an upper bound on S, this clearly doesn't work anymore, right? Because every single one of these values over here is larger than W. It's no longer an upper bound. So W is not an upper bound. By the way, folks, can you hear me? After the stream crashed, seems like oh my goodness, this internet is terrible. Folks, are you still there? Oh my goodness. Okay. All right. Well, the idea here is that, okay, so this is case one that's taken care of. W cannot be an upper bound because of the local linearity guarantees us that a little bit to the right of A is all constant. So every single one of those values has got to be an S. And therefore, W is not an upper bound on S, right? So the argument for 2 is quite similar. It's just a little bit more complicated because now we've got to talk about this case where A and B and W is some point between A and B. But the idea here is that with some W minus delta and W plus delta, remember that we're guaranteed by local linearity that every single value between W minus delta and W plus delta has some constant value c, right? And the thinking goes that, well, because W is the supremum, the least upper bound, that means that W minus delta is not in upper bound on S, which means that you've got to be able to find some little s somewhere between W minus delta and W, right? Because W minus delta is not in upper bound on capital S, this means that there's got to be some little s in here for which everything like this is constant, right? Let's call that C underscore S. But the issue here is that because every single one of these C values, every single one of these is the same, and every single one of these is the same, and a function maps to a value uniquely, in fact, the two constants have to be the exact same value, because any point in here, has got to map to a single value, right? Which means that in fact CS has to be exactly the same height as C. Does that logic make sense? You're basically using this value S as sort of a, what do you call it? Like an in-between, an intermediary almost. You know that CS has got to be equal to f of S because S is inside big S, but you also know that f of S has got to be equal to regular C because S is close to W, right? It's between W minus delta and W plus delta. Yeah, so like the way to think about this is basically, to explain this again, the thing that you're kind of afraid of is that so W minus delta to W plus delta, because of local linearity, everything in here maps to some value, we'll call it, maps to some value C, right? Again, this is like a 2D grid where the x values are on the x-axis and f of x values are on the y-axis. So everything in here maps to some value C, right? And because we guaranteed the existence of some s between W minus delta and W, right? Little s being inside big S, by definition, means that there's some constant from A to S, right? And let's call that, how do you put it? Remember, the fact that little s was inside big S means all x between A and S map to some constant, let's call it C of S, right? And the fear is that C of S and C are at two different heights. But in fact, if we look just a little bit more closely, we realize that because S is sort of in both of these sets, right? F of S has got to be equal to C, and F of S has also got to be equal to CS, which means that, in fact, these can't be different heights at all. They've got to be the exact same height. You see what I mean? What exactly is the problem that you are talking about? The York Uni. But yeah, once we go over this problem, we can talk about another one. But yeah, that's the idea here. You basically just gotta, this problem is basically asking, all comes down to showing that the two constant heights are in fact the exact same constant, right? Your fear is that they might be two separate heights, but the fact that f of s is equal to both heights means that the two heights have got to be equal. That's the whole idea. Right. It's an exhausting proof to think about the first time, but it's really not so bad once you understand it. But I guess that's true of anything. But once you're done with that, you should be able to argue that, okay, well, now all this stuff is the same constant height, And all this stuff up to W plus delta is also the exact same height. Right? So just take anything between W and W plus delta. Let's maybe call it, I don't know, Z. Right? Well, between A and Z, everything is constant now, which contradicts the fact that, which means that Z is an element of S. So W is not in upper bound because Z is greater than W. Right? So that's the idea here. The gist is that after we've shown that these two separate constant heights have got to be exactly the same, well, then we can conclude to ourselves that, okay, if we look to a little bit to the right of W, between W and W plus delta, all these values have got to be inside S as well. So W cannot be an upper bound. And that's exactly the right idea. Okay, so this proof is really long-winded and requires some careful argument, right? I'll let you work through the idea of the last thing that needs to be shown is that B is not just the least upper bound, but that B actually belongs to S. I will let you work through the rest of this yourself. I'll let you go through that argument carefully on your own. But the reason why I wanted to talk about this part is because this is what's different about the locally linear part that you're asked to work on, right? The local linear part is basically saying, okay, now instead of functions being, so if this is A and this is B, instead of everything being constant, now everything is linear, right? Everything is linear. So if this is like f of A and this is f of B is up here, the idea that you're trying to show is you want to show that there's like one single line that connects everything in between here, and that f is just this linear function. F is equal to ax plus b. This is the goal, right? But all you know is that this piece over here is linear, this piece over here is linear, and for some arbitrary point in here, it's linear. But the issue is that these might all be different slopes and intercepts, right? The issue is that at a glance, these might all be totally different lines. And to go through the proof again, it's very, very similar. But the key difference is that before, when we were doing a W minus delta, and a W plus delta, we would think and argue to ourselves that, okay, what did we say earlier? We said that because we assumed that W was a supremum, a least upper bound, that means that W minus delta is not an upper bound, which means that some value S here must be between W minus delta and W. So S, you're probably going to want to do something similar, right? S is like all the right endpoints. So instead of being constant this time, all the right endpoints, little s, what's going on? Such that, x being between A and S forms a linear function. Yeah? Well, the reason that, excuse me. So this S is going to map to somewhere around, here-ish maybe, and it's got a little bit of local linearity as well. But the great big fear, this S being here means that it gets to map to all the way originally back to A, right? Because from A to S forms a nice linear function. So basically the fear here is that, okay, we have a line over here that looks like this, and we have a line over here that might have a different slope and a different intercept, right? the fear here is that it's possible for these two lines to collide, but still be separate lines. You see what I mean? It's possible, it's at least at a glance, it's possible for this line over here, let's call this L2, and this line L1, it's possible for L2 to contain both the S and F of S point, as well as the W and F of W point, while being a different line than L1. And this is true because, how do I put it into words exactly? This is true because constant functions, if you knew that a constant function, like if you knew for a constant function that f and g agree at some point, then they've got to be the exact same constant function, right? So having a single point of agreement, s, was enough to show in the previous version that f and g were the same function. Now that they're linear functions instead of constant functions, you need a little bit more than just one point of agreement. You need 2 points of agreement, right? This is like middle school Algebra 1 or Algebra 2, because 2 points of agreement, or 2 points, should totally specify a line, right? Does that sound familiar from middle school? So that's the big idea here. You need more than 1 point of agreement. You need more than 1 point of agreement. The hint tells you that just a single S isn't going to cut it anymore. So in fact, you're going to want to choose probably 2 S's. And the idea here being that if L2 and L1 both contain the S1 and S2 points. So this point here is like S1, comma, F of S1. And another point over here being like S2, comma, F of S2. The idea is that if both of these lines, L1 and L2, contain S1, F of S1, and S2, F of S2, well, in fact, they've got to be the exact same line, right? Do you remember this pattern from like middle school where a single value is enough to totally specify a constant function, but like 2 points is enough to totally specify a linear function, and 3 points is enough to totally specify a quadratic function? It's just this exact same pattern being used here in the language of calculus, which is making things kind of confusing. But the kernel, the idea here, is actually quite simple, that you've probably seen in 8th or 9th grade before. Folks, how do you feel about this? So, I think I've provided some ways to get started. I think a lot of people have told me that they were struggling with this problem. Are you sort of seeing the intuition here? Are you all still there? I have no idea if my internet connection is any good right now. How are you feeling? Folks, on a scale of 0 to 10, how are you feeling right now? Oh, gosh. What is the difference between the set S for the constant and linear function? You define it in a very similar way. In the constant function example, capital S was basically the set of all little s, all of the right endpoints, such that the interval a comma s was constant when you put those points into the function. Now, instead of constant, it's all the little points s that are the right endpoints, such that a comma s is a linear function, such that everything between a and s is a linear function. It's basically saying, so if this is a and this is f of a, it's basically saying that it's all the right endpoints such that this is linear. That's the idea. So let's say that you had some function going upwards like this, up to like 0.5, and then it starts doing all this wacky stuff over here, and it's no longer constant, right? So in this case, I would say that capital S consists of everything from a, I guess it's a is equal to 0 in this case, all the way up to 0.5, but nothing beyond it. Yeah. So this is a reasonably challenging problem, right? And I think it definitely takes a little bit of mulling over to kind of see the idea here. But at its very core, it's an idea that you've definitely seen before in Algebra 1 or maybe Algebra 2, where having 2 points of agreement will totally specify a linear function. And this is a slightly more complicated version of the same principle, where for the constant functions, 2 different constant functions, where a constant function is totally specified by a single point, right? So hopefully that key idea makes some sense. And if anyone is still confused, you can feel free to join the Discord and ask some questions, and I will be happy to clarify. This question took me a little while to see. I was being very stubborn, and I was trying to do it all in my head. I was trying to do this without drawing anything at all, only using visualization in my head, and I couldn't quite see why you needed an extra S until I drew it out. But once I did that, I think the idea hopefully becomes reasonably clear. Yeah, like the whole goal, remember, keep your eye on the prize, the whole goal is to show that the entire thing is a big old linear function all the way from A to B. It's just a straight line with some slope, possibly. Right? Well, again, we do this by taking some W. You know, the hard case is case 2, where the least upper bound is between A and B, non-inclusive, and we basically have to show that this is impossible. Because once we can show that L1 and L2 are the exact same line, that means we can ride this line just a little bit past W, in between W and W plus delta, and conclude that if this entire thing was a nice linear function, then W is no longer an upper bound, because all the stuff over here is also an S. Right? You get to rule out case 2 that way. So much of the logic is really, really identical. You just have to carefully argue why you need more points compared to the first case. Why you need an extra S. So their hint is actually really, really good. Right? I'm basically just restating their hint visually. And hopefully you can take a crack at it. So, ready to move on? Someone else was asking about a different problem that they put in the York students part. Which problem was that? Ah, yes, the thing about the first derivative test, right? First derivative test. Yeah, I thought about that for a couple of minutes, and I didn't work through it myself, but it seemed very believable. Sure. Wait, where did that question come from? Sorry, I've definitely had some allergies and some sniffles. Different pollen. Yeah, we can move on. Sure. Let's see. Someone was asking about some first derivative thing. Where did that question come from? Where did that question, Wait, where did you get that question? Is that a homework question? It's from homework. Oh, wait, is there a new set of homework already? Oh, do you have 2 sets at once? That's funny. Yeah, sure. So question 2 is basically using this exact same idea of a set, right? They don't call it capital S anymore, but they're saying that if f is a function with domains 0 and 1, so Q2, Q2, if f has domains 0 and 1, and x is the set of all, so capital X is all little x in 0 and 1, such that f is continuous. So again, it's like little x is all the right endpoints It's all the right endpoints of all the intervals that are continuous. It's all the right endpoints of intervals on which f is continuous. So like doing some examples here, right? From 0 to 1, if I was drawing out a function like this all the way up to 0.5, and then it just went like that, I would say that all these points in here are inside big X, because look at them, right? They map to... sorry, this isn't the right way to visualize it. If you view all these points as right endpoints, the function is, and 0 is the left endpoint, the function is continuous on these intervals. But the moment you get over here, it's no longer continuous because of this gap, right? Yeah. Does this make sense? That's the vision that we've got. This is what the setup of the problem is. And they're basically asking you to come up with a counterexample or show that the assertion is false, right? They're saying let S is supremum of capital X. Then, they're claiming that F is continuous at S. So, I don't know. I don't think there's anything really crazy here. Without trying to give it away, I'm suggesting you come up with examples